What if the real danger wasn't the rain, but the land it was falling on? The recent catastrophic flood in Kerr County, Texas wasn't just a weather event, it was the end result of a perfect storm of geology, terrain, and climate coming together in the worst way possible. And now, scientists have cracked open the truth behind it. And it's not what most people think. The images were everywhere: cars swept away, homes
If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment. Your feedback helps shape what we cover next, and you being here keeps the conversation going. Thanks for watching. See you in the next one.
submerged, entire streets turned into rivers. But this wasn't just a case of too much rain. This flood was a textbook example of how the land itself, its bones, its shape, its history can turn a storm into a full-blown disaster. And the science behind it, it's mind-blowing. Let's start with the basics. Kerr County sits in the heart of Texas Hill Country, and on the surface, it doesn't look like the kind of place that would be especially vulnerable. It's not sitting at sea level, it's not surrounded by major rivers, and the terrain isn't wildly mountainous. But that's exactly the problem. This area is built on a foundation of limestone. That rock may look solid and unassuming, but geologically speaking, it's a key player in this disaster. Limestone, especially the kind found in Kerr County, is layered and shallow, with poor soil coverage on top. That means when it rains, the water doesn't soak in, it slides right off. And when you throw hardened, clay-rich soils into the mix compacted by the region's semi-arid climate, it gets even worse. These soils act like a seal. So instead of rainfall soaking into the ground like a sponge, it's more like pouring water onto concrete. Now factor in how flat the terrain is. The county doesn't have steep slopes that slow water down, it has a high drainage density. Translation: a dense web of tiny channels, all working together like a hyper-efficient plumbing system. Except instead of managing the water, it dumps it fast and hard into a few major rivers, like the Guadalupe. And here's where the tech comes in. Scientists used advanced LiDAR imaging, essentially a kind of laser scanning, to take a super detailed look at how the land is shaped. What they found was shocking, subtle but widespread channels hidden in the landscape that guide water flow during heavy rain, forming broad sheets of water that move fast. These shallow features don't show up on standard maps, but during a flood, they matter a lot. This type of flooding is called sheet flow. It doesn't start with a trickle in a ditch. It starts with entire swaths of land getting submerged in moving water all at once, and then converging into rivers that are already overwhelmed. It's fast, it's brutal, and it gives almost no warning. So when that record-breaking rainfall hit, it wasn't just about how much water fell, it was about where it fell. In Kerr County, even small shifts in the storm's position can mean the difference between a manageable overflow and a full-scale catastrophe. Because of the terrain's uniformity and high drainage density, water gets funneled in the same direction with shocking speed. Now contrast that with places like the Appalachian Mountains. Over there, you've got deep soils, complex bedrock, folded and weathered hills. It's a geological jigsaw puzzle. And that complexity actually slows things down. Water moves more gradually through those systems, which means fewer flash floods. But other problems emerge, like debris flows and landslides. In Appalachia, the storms don't always flood streets in minutes, but they do destabilize slopes and trigger slides that carry entire chunks of landscape downhill. It's a slower burn, but just as dangerous in its own way. So while both regions are vulnerable to extreme weather, the way that weather plays out is dictated by the geology beneath your feet. Back to Kerr County, what makes its situation even more intense is the role of drought. This area swings between dry spells and heavy rains, and during the dry periods, the soil bakes, compacts, and becomes even less permeable. That means when the rain does finally come, there's no absorption at all. It's runoff city. So when you zoom out and look at the big picture, what caused this devastating flood wasn't a freak storm. It was the outcome of millions of years of geological formation. The limestone bedrock, the thin soils, the flat landscape, the dense drainage system, and the baked-in effects of drought, they all collaborated to create a worst-case scenario. The truly wild part is that these elements are baked into the landscape. They don't change. The climate may swing, the storms may vary, but unless there's a massive shift in the land itself, this risk is permanent. That's where the science gets practical. By understanding how these landscapes react under pressure, how rain moves through them, how the water channels operate, How the soil behaves. Experts can start to predict flood behavior with more precision. It's not enough to just track how much rain is coming. You have to know how the ground will respond. Because not all rainfall is created equal. A 2-inch downpour in the Appalachians might trickle through the roots and rocks without much fuss. But in Kerr County, that same 2 inches can set off a chain reaction that ends in submerged neighborhoods and emergency evacuations. It also raises big questions about urban planning. How do you build infrastructure in an area where the ground can't absorb water? How do you set up warning systems when the flooding happens this fast? How do you prepare a population for floods that don't start in rivers, but on wide, open terrain? That's why scientists are calling for more localized flood assessments. The old one-size-fits-all model doesn't work anymore. A floodplain map based on rainfall averages can't tell you what's really going to happen when the water hits compacted clay over shallow limestone. You need LiDAR. You need geological history. You need micro-level data. And then there's the public education side. Most people think floods come from rising rivers. That's not always true. Sometimes, the danger comes from the land itself, from the way it shrugs off water and channels it downhill like a fast-moving conveyor belt. And unless communities understand that, they're not going to be ready. Because here's the thing, Kerr County won't be the last place this happens. As climate patterns shift and storms become more intense, other regions with similar geological profiles could be next. Places with shallow bedrock, hard soils, and flat terrain need to start paying attention. Because if the land is already set up to fail during a storm, the consequences are just waiting for a trigger. And that's what makes this flood so important. It's not just a local disaster, it's a wake-up call. It shows how much of our risk comes not from the sky, but from the ground. It proves that understanding geology isn't some academic side quest, it's survival. So the next time you hear about a flood, don't just look at the rainfall totals. Ask about the soil. Ask about the bedrock. Ask how many little drainage channels are hiding in the terrain. Because that's where the story really begins. Let us know what you think in the comments. Did this change how you see flood risks? Have you experienced flooding in your area that didn't seem to come from the usual sources? We want to hear your stories. And if you found this breakdown eye-opening, don't forget to like, share, and subscribe. We've got more wild disaster deep dives coming your way. Stay safe, stay smart, and stay curious. So here's the part no one wants to hear. This wasn't a freak event. The Kerr County flood didn't break the rules of nature, it followed them perfectly. That's what makes it so terrifying. Because when you strip away the shock, the viral footage, the helicopter rescues, and the gut-wrenching damage, what's left is a natural system doing exactly what it was built to do. It's just that the system was never built to handle us. Homes, roads, businesses, we've been building on a foundation that's been warning us for centuries. We just weren't listening. Let's go back to the geology again, because that's the real culprit here. Underneath Kerr County is a network of limestone layers laid down millions of years ago when this region was covered by a shallow sea. Over time, those layers hardened into what we now call bedrock. But here's the catch, this bedrock is full of fractures and cavities. It's not spongy. It doesn't soak up water. It directs it. Like a marble countertop tilted just enough to send every drop toward the edge. Then add the soil, or more accurately, the lack of it. The topsoil in this area is notoriously shallow. It's thin, patchy, and in many places, it's barely more than a dusty coating over stone. Combine that with the hardened clay from drought cycles, and you get a landscape that actively resists absorption. The moment rain touches down, it's on the move. And it doesn't move randomly. That's where things get spooky. LiDAR imaging revealed that the land is carved with faint drainage patterns, channels so subtle you'd never see them with the naked eye. But during a storm, these invisible veins turn into superhighways for water. They pull everything downhill into creeks, then rivers, and eventually, into overflowing disaster zones. So while people were watching the skies, worried about how much rain would fall, the real danger was already baked into the ground. That's the trap. When you only look up, you miss what's right beneath your feet. This is why comparing Kerr County to places like the Appalachians is so crucial. Not because one is worse than the other, but because it highlights just how differently landscapes react under pressure. In Appalachia, you've got complexity. Mountains formed by ancient tectonic collisions, folded rocks, deep loamy soils. It's a geological maze. And when it rains, that maze slows the water down. It pools, it seeps, it filters through layers before causing trouble. But that same complexity also means it's prone to landslides. The soil may be deep, but when it's saturated, whole hillsides can give way. Debris flows aren't fast-moving water, they're avalanches of rock, trees, and mud. They'll take out anything in their path, but they tend to come with slightly more warning than a Kerr County flash flood. Slightly. Back in Texas, there's no such delay. Kerr's drain is like a launch pad for runoff. It's flat, it's open, and its drainage density is off the charts. That means there are lots of tiny tributaries packed into a small space, and they all work together like a hive mind. Once the rain starts, the water moves fast and in one direction. That's what scientists mean when they say the region has high drainage efficiency. It sounds like a good thing, right? Efficiency. Not here. In this case, it means every drop of rain is being delivered to the rivers with very little friction. And when that system gets overwhelmed, the consequences are immediate. Water doesn't rise gradually. It erupts. Here's another layer. The semi-arid climate. Kerr County lives in this strange in-between zone, not quite desert, not quite humid. That means the soil spends part of the year baking under the sun, forming crusts that are practically impermeable. Then, when rain finally arrives, it behaves like hitting a wall. There's nowhere for the water to go but away fast. And that dry-wet cycle also means erosion is a constant issue. Over time, the terrain has been smoothed and simplified. Not a lot of variation, not a lot of rough terrain to slow the flow. When scientists say Kerr County's landscape is structurally simple, they're not being poetic. They're describing a dangerous uniformity that gives water an open runway. Now, you might be thinking, okay, but doesn't every place have its own flood problems? Absolutely. But what makes Kerr County and regions like it so vulnerable is how predictably explosive its response is. When you know what the land is made of, and how it channels water, it becomes clear that floods aren't just possible, they're inevitable. And that's why the recent flood was so devastating. It wasn't just the volume of rain, it was the precision. Where the rain fell in relation to the watershed boundaries turned out to be everything. A slight shift in storm position meant the difference between a river swelling and a river breaking loose. This is the kind of nuance most flood models don't account for. Traditional flood maps look at elevation, rainfall averages, and past events. But they don't always dig deep literally into what the ground is made of. And without that information, you're flying blind. That's why LiDAR was a game changer in this case. It let scientists strip away vegetation, buildings, and even surface distractions to see the true shape of the land. And what they found were microchannels, hundreds of them crisscrossing the landscape like hidden scars. These channels aren't visible in normal aerial imagery, but during a storm, they dictate everything. It's almost surgical. The water doesn't just flood randomly, it follows ancient paths carved by millennia of erosion, tectonic shifts, and sediment movement. These paths might be subtle, but their impact is massive. So when people ask, what caused this flood? The real answer isn't the storm. It's the system. A system of rock, soil, climate, and time, all converging in a moment of brutal efficiency. But that doesn't mean nothing can be done. In fact, understanding this system is the first step toward protecting people from it. When you know how water will move not just generally, but exactly, you can design better infrastructure. You can build smarter drainage systems. You can plan development in ways that don't put homes directly in harm's way. It also means local governments need to rethink how they assess risk. Broad models and generalized flood zones don't cut it anymore. What's needed are hyperlocal assessments, block by block, even property by property. Because in places like Kerr County, the line between safety and disaster might be just a few feet of elevation or a forgotten drainage ditch. And that brings us to the bigger lesson here. Natural disasters don't just happen. They're the final act in a story that started long before we got here. The Kerr County flood wasn't the beginning of anything, it was the result of an ancient script written in limestone and clay. The storm just turned the page. The key now is not to be shocked, but to be prepared. And that starts by respecting the land not just aesthetically, but scientifically. Understanding the geology, the history, and the subtle signals the terrain gives off. Because there's a hard truth here, climate extremes are becoming more common. But that doesn't mean every flood will look the same. The way the earth receives that storm will dictate how bad it gets. And in places like Kerr County, where the land itself invites the chaos, awareness isn't optional, it's survival. Now here's where things get uncomfortable, not just for residents of Kerr County, but for a lot of people living in similar landscapes across the country. Because this isn't just a Texas problem, it's a geological blueprint. Anywhere with a similar mix of shallow and permeable soils, flat terrain, and a dense drainage network could be sitting on the same ticking time bomb. And unless local governments start paying attention to the underlying causes of floods, not just the surface symptoms, they're going to keep getting blindsided. This isn't a case where sandbags and storm drains are enough. If your entire terrain is built to reject water and accelerate runoff, then traditional mitigation just won't cut it. You need comprehensive planning that factors in not just rainfall, but bedrock structure, soil chemistry, and hydrologic response. And that's where most systems are still behind. For example, many existing floodplain maps are based on outdated models that don't account for modern technology like LiDAR or high-resolution topographic analysis. They show you where water might go based on past behavior, but not where it will go based on the terrain's precise structure. And in a place like Kerr County, those gaps in understanding can be deadly. That's why the takeaway here isn't avoid floods. It's understand your land. Know how it behaves. Know how it reacts under pressure. Because this flood didn't happen because the weather was weird, it happened because the land was primed to fail the second the rain arrived. And once that water started moving, the flood didn't unfold in stages, it erupted. Think about how fast everything changed. What began as heavy rainfall quickly turned into a full-scale disaster. Rivers surged. Tributaries became torrents. Water didn't rise gently, it shot forward like it had a mission. And it did. It was following a blueprint laid out by millions of years of geological evolution. That's the part that still doesn't get talked about enough. We spend so much time focusing on short-term weather patterns, but we ignore the long-term landscape patterns that tell us how a place will behave when things go wrong. And Kerr County, it was practically screaming for help. The limestone bedrock, the shallow clay soils, the high drainage density, the flat terrain, the semi-arid climate that compacts the earth into a crust. All of these pieces have been there the whole time, working together to create a system that looks stable until it isn't. And this is where we have to talk about responsibility. Because yes, nature played its part, but human decisions made things worse. Development that doesn't account for hydrology. Roads and buildings constructed in high-risk runoff zones. Ignoring the subtle signals in the landscape because they're not dramatic enough until they are. It's easy to treat floods like one-off disasters. But when the land is this prone to rapid, catastrophic runoff, floods are not anomalies. They are consequences. And if there's any hope for the future, it's in the science. The fact that researchers are using LiDAR to map terrain down to the centimeter, analyzing soil behavior in specific microregions, and comparing geological histories between regions like Texas and the Appalachians, that's where progress starts. If you've made it this far, let's hear from you. Are you living in a region that might have similar geological risks? Have you seen local infrastructure that clearly wasn't built with this kind of science in mind? Drop a comment. Share your thoughts. And definitely subscribe if you want more breakdowns that go deeper than the headlines. Because next time, it won't just be about what's in the forecast. It'll be about what's already written in the earth.